Hello everybody, welcome back to the course on quantum field theory, a first course on quantum field theory and quantum entanglement. So, the topic we have been looking at is canonical quantization of scalar field last time when we stopped essentially. So, I introduced you various concepts like how do you write elements, essentially I introduced you the concepts of classical field theory. So, we have been looking at canonical quantization of the scalar fields. So, in the review of just to give you a review of what we did last time. So, we did introduce the Einstein indices, how to write it in terms of relativistically in relativistic notation, relativistically invariant scalar field theories. So, in which we wrote down how to write the Lagrangian density, and then we looked at how to write the action, how to count the dimensions of these things, of these fields, and then we also looked at how to write the Euler's Lagrange's equations of motion, and we derived the conjugate momenta for the conjugate field. Essentially, what is a conjugate momenta field? So, for a given the scalar field, essentially for a given scalar field. Then we looked at how to write the equations of motion, and finally we derived the canonical quantization conditions. Essentially, these were the canonical quantization conditions. Along the way, these are the canonical quantization conditions between the field and its conjugate momentum. Along the way, we also looked at how to write the Hamiltonian, the total Hamiltonian, and the dimensions of the mass dimensions of the field in the natural units of h cross and c is equal to 1. So, today we will continue with this the consequence of this canonical quantization on the fields. We will continue with this, and then we will try to attain at a particle interpretation of the as a consequence of the canonical quantization. So, canonical quantization of the scalar field, which is continued in today's lecture. So, our this to recap, our scalar field is phi of x t, and our canonical conjugate momenta is pi of x t, and the quantization conditions are given by this. Essentially, del cube is essentially for x, y and z. If you want, we can put bars, okay, on all these things. Okay. So, this is, and then of course, you can have x t phi of x prime t 0 0. And what would we call these conditions? So, these are all at the same time. So, we call this as equal time canonical commutation relations. So, these are equal time canonical commutation relations. This is something which you should remember. You can give an acronym and everything, but it is not important. It is just important that we should remember that they are at the same time essentially. Okay. Now, we want to see what this phi field is essentially. What is a phi field? Before proceeding further. So, phi field should not be considered as a single dynamical variable. It should be considered as a collection of dynamical variables phi of x t dynamical variables. Okay. So, these in classical theory, now you want to promote them into quantum theory essentially. So, they end up being in quantum theory they should be considered as operators. So, the field itself is an operator, okay, the field itself is an operator. So, the field phi of x you can consider so you can consider linear combinations of these operators continuously essentially, instead of you can write a collection of these operators. So, in other words what we are doing, okay, you can take phi of k bar t is equal to yes e power minus I k x k bar dot x phi of x t. So, my phi has to maintain the same symbol everywhere. So, you take the scalar field, and what we did is essentially a Fourier transform. Essentially you are taking a collection of these fields essentially, okay, or if you want a collection of these dynamical variables and re-expressing it in terms of its conjugate momenta or k, it is a Fourier transform. So, pi tilde of k of t, okay, is d cube x e power minus I k of x pi of x t. So, for both the field and its conjugate momentum field, you can think of the operators in the k space phi tilde and pi tilde essentially. So, that from the this is essentially what we did was a Fourier transform. So, you should consider them as a collection, and so if you consider them as a collection, you can use Fourier transform to represent the k space operators, the case momentum space operators, as we do in quantum mechanics. So, these are your position space operators and the corresponding momentum space operators. Now, they can be, you can do the inverse Fourier transform. And one gets, this is easy to see, Now, this is just the inverse Fourier transform. So, from the inverse Fourier transform you can get back your phi of x t in terms of the pi tilde of k of t essentially, and the same thing also holds for the pi, the conjugate momenta. Now, so what we have is there are some interesting relations you can think of, like for example pi of x t, okay, I had to be careful with my notation. I am introducing phi and pi interchangeably. Okay, I hope I am doing it correct. Okay, here it is fine. I have to be careful with my notation. Okay, so pi of so now what happens is we started with a real scalar field. So that means so phi of x t, so it does not have any imaginary components, it is a real scalar field. So it turns out for a real scalar field, a Hermitian operator, because it is a Hermitian operator in H tilde, phi tilde, so phi tilde of minus k bar t is equal to phi dagger k of t. So you have this nice relation essentially that phi tilde phi of k, which we have essentially. So phi tilde of minus k is nothing but phi dagger, okay, just purely from the Hermicity, from Hermicity. Now this changes for a complex scalar field, okay. For a complex scalar field this does not happen essentially, okay. And then we have the Heisenberg equations of motion. This I hope you all understand, this is a very standard relation, because you have phi dagger of k is equivalent to phi tilde of minus k essentially. So this is just by the Fourier fields essentially, just from the Hermicity operator. The Heisenberg equations of motion So the Heisenberg equations of motion can be written in this particular fashion, and they are the same as the classical equations of motion. Now I can write for the Fourier transform field, if I put it back into this equation, for the Fourier field in momentum space I1 has del square phi tilde k of t by del t square minus plus del square becomes k in momentum space. So this just becomes k square plus m square phi tilde of k t is equal to 0. Now this equation of motion is nothing but your Klein-Gordon equation of motion, okay. You can I think all of you realize that this is nothing but your Klein-Gordon equation of motion. Which you must have done in your relativistic quantum mechanics course or quantum mechanics and the relativistic framework essentially. So just put back the momentum space fields. This is what we do also in the same thing, and for this the general solution, most of it is already covered for you in if you do your relativistic quantum mechanics course. So but anyway, let us do this. This is just the dispersion relation of the wave, and this gives me the general solution. The general solution can be written as is given by So, you know because this is nothing but your Klein-Gordon equation of motion, whose solutions are nothing but your plane waves. So, you can write these plane waves essentially in momentum space. You can express it in terms of momentum space, phi tilde kt is equal to. So, you can take some phi 1. Okay, I am doing the same mistake as always. So, I had to use phi tilde k of t. So, the solutions for this relativistic equation of motion, there are two, one is e power plus I k t and another is the e power minus I k t. You all know this thing between your relativistic wave equation. So, which you can write it as phi 1 or phi 2, okay, phi 1 of k e power I omega p t. I will tell you what is omega p, nothing but it is the energy or the frequency or pi 2 of k e power plus I omega p t, okay, where omega p is root of k square plus m square essentially. And the reality condition, because we have pi tilde of k t dagger is equal to pi tilde minus k t, we have pi 2 k bar is equal to of k is equal to pi 1 dagger minus k. Okay. This is nothing but your energy or E essentially, or you can, because which is nothing but h cross omega, omega p is the frequency, and there are two plane waves, the forward going plane wave and the backward going plane waves. This is all which we write down in for the standard solution for the Klein-Gordon equation. Okay. Independent of that, you can see that this is the relativistic wave equation and which has these two solutions essentially. Now, you can write this using this condition that of the reality of the wave function. This expression just becomes phi tilde of k t is equal to phi 1 e power minus I omega p t plus phi 1 dagger minus k, this should be plus k. Okay, let me expand it. This is going to be important, and this will be the crucial difference between a complex scalar field and a real scalar field. Phi 1 k bar e power minus I omega p t plus phi 1 dagger minus k bar e power I omega p t. Okay. So, it is the same phi 1 and phi 1 dagger which appears for as coefficients of both the forward going and backward going wave essentially, or okay. So, for the both negative and positive energy solutions. From your relativistic quantum mechanics class, you know that there are two solutions for the relativistic wave equation. One is associated with the particle and antiparticle. For the real scalar field, there is no antiparticle because it is the same thing, and that is the reason why we have the same wave function sitting on both forward going and backward going wave function. There is no antiparticle for the real. We will do the charge scalar field in a second essentially in once we finish this real scalar field. There you will see an antiparticle and it will have a different set of wave functions. For a real scalar field, there is only one set of wave functions essentially. So, now we see what happens for pi, the conjugate momentum. this is given by, with this expansion, I omega p phi 1 of k e power minus I omega p t plus I omega p phi 1 dagger minus k e power I omega p t. So, we can derive pi directly from this, and so with this you can express this you can express the full wave function, or for, so you can solve for phi 1, okay. From this one can solve for pi 1 of k, and this is given by what is phi 1 of k. You can solve this, and this is given by integral d cube of x e power minus I k dot x minus omega p t phi of x t plus I by omega p pi of x t. Now, we can actually look at the canonical computation relations. Now, we know what are the canonical computation relations between phi and pi. Now, we can ask the question, what are the canonical commutation relations in the momentum space for pi 1. So, for pi 1 k and phi 1 q, you have the canonical commutation relations as follows. So, instead of x and y, okay, instead of x and y, we are taking the momentum space wave functions pi 1, and because there are no two, pi 2 is the same thing as pi 1, a dagger essentially. So, we are just taking as pi 1, but in terms of, instead of single momenta, we are taking in terms of two momenta k and q. Now, I will ask you to guess what is the answer without okay, you can try to guess the answer, and okay, since I cannot know what your guess is, but I am guessing that all of you will guess it right. So, what I am going to do is I am going to substitute what is the definition of pi and what is the definition of pi, capital Pi, both into this expressions, and so this gives me e power minus I k bar dot x bar minus omega. So, one of the momentums is k, so this is omega k t, okay. The other one would be e power minus I q bar dot x bar minus omega q t, okay, times, expand what is pi, I know what is pi, okay, pi phi 1 is nothing but pi of x t plus I omega k pi of x t, commutator pi of y t plus I guy omega q pi of y t. So, I just use the previous expression. So, this is the expression we have for pi 1. So, I am just evaluating the commutation relation for pi 1 at q and pi 1 at k. Okay, that is what I am just using this expression. Now, I know what are the commutation relations between pi and pi, phi and pi, and I also know what is the relation between phi and pi. Okay, because these are the commutation relations I already imposed essentially. Now, you can evaluate this and you will end up with the relation essentially 1 by 4 h cross is equal to 1 and everything d cube of x e minus psi k plus q dot x bar minus omega plus omega q times t. The only non-zero thing would be this, okay, everything else will go vanish, and the only non-zero things would be just 1 by omega k, the coefficient essentially, minus 1 by omega q. To know what is this essentially, if you remember your identity of a delta matrix, a delta function, you know that e power delta this thing is nothing but your delta function essentially. So, e power I k, integral of e power I k x of del cube of x is delta of k essentially, okay, delta of x. So, this is the same thing, you can use the identity this is nothing but your delta function So, you can put it back into this, and what you will say, lo and behold, this will be just 0. This is precisely what we expect essentially. This is precisely what we expect. Okay. In the momentum space commutation relation, if I take phi and phi of k and phi of q, I should get back 0. This is what we expected, and we see that you get back this. And similarly, if you calculate the momentum space commutation between k and phi 1 dagger of q, now again I will ask you to guess. So, you will know that this should not vanish, because what we know, this should be 1 by 2 omega k delta cube k minus q. So, now you can ask what happens for, okay. So, this is the equivalent of phi and pi, the commutation relation, but now in momentum space, this is the relation in terms of phi and pi. So, this means that then you also have phi dagger k, phi dagger q, which should vanish, which should also fit now. Why is this important? Why this is important is because now we are reaching the conclusion that how to connect this with a harmonic oscillator raising and lowering operators. Now you see that this phi is very much like the annihilation operator A, whereas phi dagger is like the A dagger operator, essentially is like the A dagger operator. So with this you can define the annihilation operator, the annihilation operator given as A of k is equal to 2 omega k by h cross. So, h cross is nothing but 1. So you can remove this. Okay. So with this you have your definitions for the annihilation operator, and so the commutation relations what we derived so far would just become A of k, A of q is equal to 0, A of k, A dagger of q is equal to 2 pi whole cube delta cube k minus q. So with this I have now successfully quantized my scalar field in terms of these harmonic oscillators given for each momentum k or each frequency omega k, omega p, whatever essentially. So I can express by the total field phi of xt. This is the most important relation, cube k cube root of 1 by 2 omega k A of k e power I k x minus omega k t plus A dagger of k e power minus I k bar dot x bar minus omega k t. Okay. So now I can I can change them okay. So you can always write the second term into minus pi and everything, and you can express this entire thing. Okay. So this is the most fundamental step. Okay. So what we have is the scalar field phi, expressed in terms of A, which is an annihilation operator, but for every k, a real scalar field in terms of for every k, a bunch of annihilation operators. How many of them are there? They are k dependent, integrated over k. Okay, they are k dependent, integrated, and then this is k dagger. This is A dagger, and so you see that this is given by a bunch of these A and A dagger operators, each for every momentum, essentially for a bunch for every momentum. Okay, for every momentum you have a or if for every frequency you have a harmonic oscillator. So the scalar field is given in terms of a infinite number of harmonic oscillators, each with its own annihilation and creation operators, and for every frequency, meaning in the sense for every momentum mode you have a harmonic oscillator. So how many momentum modes you have? Infinite momentum modes. So you have infinite harmonic oscillator, and each of these harmonic oscillators has its own spectrum, essentially. Okay. Conjugate momentum density, you can write pi of xt also in this particular fashion. Essentially you can write what is it in this particular thing. Okay. So this pi of xt is equal to minus I integral d cube k by 2 pi cube root omega k by 2. So, have a of k e power I k bar of x t minus omega k t plane wave part minus a dagger k e power minus I k bar dot x t minus omega k. Always remember, by writing this I use the identity that minus k is equal to a dagger, essentially minus k a of minus k is equal to a dagger of positive k. Okay. So, both the field and its conjugate momentum are expressed in terms of creating operator and also the creating operator, which is a dagger, and the annihilation operator a. And this is the first step for the canonical quantization. Okay. So, to see the consequences, we will see in the next lecture how these consequences of this. So, this lecture has been a little bit formal. We just had a lengthy derivation, essentially. We just had a very long derivation, but the calculation is very straightforward. Is extremely straightforward. What we did to begin with, we wrote down the Hamiltonian and the Heisenberg equations of motion. From the Heisenberg equations of motion, we wrote it down in terms of the field space, in terms of the momentum space. From the momentum space for the field, from the field space we wrote it down into momentum space, and then we used the, before that we used the Fourier transformations of these fields and corresponding conjugate momentum. Okay. And field, because it is a real scalar field, phi dagger is equal to phi. So, phi dagger is so we can express the phi dagger of minus k in the momentum space to be equivalent to the phi dagger of plus k because of the Hermiticity. Okay. Because of the operators. Okay. Okay. Now, we use the equations of motion, wrote down its full form, essentially what is it, the solutions in terms of the plane waves. We then re-express using the solutions of this plane wave, because we do not have phi 2 as a separate independent variable, because it is a real scalar field. The phi 2 just becomes phi 2 is equal to phi 1 dagger of minus k. Okay. For the, you can just see that it just becomes that. Then re-express the original phi 1 of k, phi tilde of k and phi twiddle of k in terms of phi 1 and phi 1 dagger. Using this, we wrote it down and we express the original commutation relations and rederive the commutation relations for phi 1 k and phi 2 k, phi 1 q, and with this we see that it just follows angular momentum algebra. Okay, it just follows angular momentum algebra, AK and AK angular momentum algebra, because in the sense that you have creation and annihilation operators exactly like what we have for the angular momentum. Okay. And this is the expressions. Now, those of you who forgot your angular momentum, I have revived it in lecture 3, I think. I have revised it in lecture 3. Okay. No, lecture 2. I think I revised it in lecture 2. So, go through it again essentially, and you see that the derivation so far has been extremely straightforward. It looks a little lengthy because I am doing it on the board, but it is very straightforward. But the end result of this derivation is your scalar field, a conjugate momentum field, are expressed in terms of A and A dagger operators of harmonic oscillators. They essentially, that means they are expressed in terms of simple harmonic oscillators of of large number of frequencies, in fact all possible momenta or all possible frequencies. Okay. Of all possible frequencies. So, each of the frequency having its own field interpretation or particle interpretation. I will stop here and we will come to the interpretation in the next lecture. Okay. Okay, thank you very much.